Good morning, everybody. It is my pleasure and honor to introduce the first plenary speaker of this ISIT, Neri Merhav. Neri Merhav is a professor at the Electrical Engineering Department of the Technion Israel Institute of Technology, where he received his 3 degrees in electrical engineering. In addition to his academic achievements, Professor Merhav has also been affiliated with AT&T Bell Labs and HP Labs. His valuable contributions have earned him the distinction of being a co-recipient of the 1993 Paper Award of the IEEE Information Theory Society and the Best Paper Award of the 2015 IEEE Workshop on Information Forensics and Security. He was recently nominated a Life Fellow of the IEEE. He also received the 1994 Award for Academic Excellence, the 1994 American Technion Society Award for Academic Excellence, and the 2002 Technion Henry Taub Prize for Excellence in Research. During the years, Neri served as an associate editor to the IEEE Transactions of Information Theory, for source coding, and for channel theory. He is currently on the editorial board of Foundations and Trends in Communication and Information Theory. In 2001, he served as a co-chair of the program committee of the ISIT. Neri's research interests include information theory, statistical communications, statistical signal processing, and the interplay between information theory and statistical physics. From personal experience, as Neri's former student, I can say that he's also an excellent teacher and an educator to generations of information theorists, some of which are faculty members in leading universities worldwide. Please welcome Neri Merhav.
Thank you, Nelia, for the very nice introduction. I want to thank also the program committee chairs for inviting me. It's a great honor, and I'm truly excited. My talk is about several techniques some of which I developed on my own. Some of them are known more to other communities, like communities of physicists, and perhaps less known in our community. The inspiration comes from my research activity in the interplay between information theory and statistical physics. And perhaps one of the main messages that I would like you to remember is that when you deal with interdisciplinary research which connects various fields like information theory and some other field, then sometimes, even if it's purely academic and purely theoretical and abstract, eventually it can lead to the ability to import analytical tools which help us to analyze concrete problems. So sometimes the wider look is also beneficial for concrete things. Okay. I would like to devote this talk in memory of a very important person, I think, for the whole community and in my personal life in particular, Professor Jacob Ziv. And I would like to remind you that tomorrow at 8 p.m. there's going to be a 1-hour event in his memory, so please come, you're all welcome. Okay, let us start. So, like everything in information theory, it all started with Shannon. The random coding, why don't it? Okay. The random coding idea started originally as a tool for proving, ingenious idea of proving the existence of good codes in some sense. That we all know. Later, in the 50s and 60s, we have the classical papers by the giants like Elias, Fano, Gallagher, and so on, on exponential error bounds, on the error probability of random coding and reliability functions. And then in the 67, we have the famous paper by Shannon, Gallagher, and Berlekamp, which also derived the lower bounds on the error probability, the sphere packing bound and straight line bound, also classical works. In the 80s, we got the great contribution of Chisar and Kerne, namely the method of types, on which I'm going to rely on this talk. And throughout all the years after, we have seen many works on improvements and extensions and application to codes with structures like convolutional codes, linear codes in general, and so on. And what is important to remember is that unlike the original idea of random coding just as a tool for proving existence of codes, nowadays it became a paradigm on its own right. Namely, people talk about ensemble performance of codes, and this is became quite customary. So let me start by talking about the tools that I developed. And I apologize in advance that this talk is going to be somewhat more technical than the average plenary talk in ISIT, because the very subject is about techniques. Okay, so what do we know about traditional bounding techniques, well known to information theorists? The first idea is that if you want to upper bound the probability of error of the maximum likelihood decoder, an easy upper bound is to replace the maximum likelihood decoder by any other decoder, which is hopefully easier to analyze, and you're done. Another well-known tool is Jensen's inequality, which is used, for example, in Gallagher types bounds, but not only. Yet another one is the idea of bounding indicator functions of error events, pairwise error events, by likelihood ratio, which is actually nothing more and nothing less than the Chernoff bound. And then we have the union bound with its various variations, simple union bound with truncation, because it cannot exceed 1, union bound with a power parameter, which is actually exactly the same as the one with truncation, after you minimize over the parameter. Union bound with intersection, which also dates back to Gallagher, I think. And all sorts of other inequalities, like what I call the power distribution inequality that Forney used in his 68 paper. So all these tools, of course, greatly facilitate the analysis and give us concrete results, closed form results. But there is a price for that, and then usually the price is that we might compromise the tightness, the exponential tightness of the associated bound. And one of the main messages of this talk is that this is not a necessity to lose tightness. In many cases, it is possible to preserve exponential tightness, at least exponential tightness, by bypassing the need to use the techniques that I mentioned in the previous slide. did I do here? Okay. So for this I have my little hammers and screwdrivers, which includes a couple of things. The first thing is a technique that I developed throughout the last decade, which I call type class enumeration. The idea is to count how many code words in the code book fall in a given conditional type, and the details will come soon. The second one, which I actually used started to use much earlier, is an analog of the method of types for infinite alphabet, continuous alphabets, and countable alphabets without recourse for quantization. But we do use the structure of the family of distribution, and I'll talk about it later. The saddle point method for assessing probabilities and volumes. This is a technique that is used quite frequently by physicists. I think it is less known in our community, so I mentioned it. Yet another thing is, if time permits, integral representations of some important nonlinear functions like the logarithmic function and the power function, which are very useful in many information theoretic applications. And finally, some recent work that I did, which I called Jensen-like inequalities. It is some sort of a generalization of the idea of Jensen's inequality, which provides quite a rich family of inequalities, sometimes reversed version of Jensen's inequality with the inequality sign reversed. And I'll be more specific later on. So here, to fix ideas, let me be concrete and give a simple example on something that all of us, I think, are familiar with. The traditional Gallagher bound for the error probability and for the probability of correct decoding averaged over all codes. In both of the cases, we have to deal with some summation of exponentially many terms, one per each code word, and the code words are random, and all this summation undergoes some nonlinear function like the power function. And the question is how to deal with it without the natural tendency to insert the expectation into the brackets and use Jensen's inequality, which might sacrifice tightness. And if this is not difficult enough, in many cases, like the broadcast channels, the interference channel, the Gelfand-Pinsker channel, the wiretap channel, and so on, the likelihood score is itself a summation over exponentially many terms, which complicates things even further. Okay, so the simple idea is this. Instead of summing over exponentially many code words, I'll replace it by a summation over polynomially few types by collecting together all code words that contribute the same score. So if they are in the same conditional type, say I'm counting all random code words which are conditionally in the same type given y, then I'm collecting them together, and then it becomes a summation over polynomially many types. So NYQ is the number of random code words in a given conditional type of X given Y. So what have we gained? First of all, instead of exponentially many terms, we have polynomially few terms. Secondly, this number NYQ is a simple binomial random variable with the number of trials is e to the nr, the codebook size, the probability of success, namely the probability of falling in a given type, is according to the mutual information, which is easy to handle. And the nice thing is that in almost all applications that I used this method, it turned out that the marginal distributions of the various NYQ, where Q runs over all types, is enough. I don't need joint distributions of several. And even in the rare cases that I need, only 2 are enough. And 2 of them, for 2 different types, are almost independent because there are many, many Qs. So it's not a problem. Just a second. Before my tongue. Okay. So here is a simple example of how to use this idea. We pass from why don't I see the spot? Yeah, we pass from the exponentially many terms to the polynomially few terms. We replace the summation by the maximum. It's exponentially the same. Then we commute the maximization with the power function, which is okay. And then we pass back from maximization to summation, and then we can interchange the expectation with the summation. And then all we have to deal with are moments of this binomial random variables, 1 moment at a time. So that's a very easy thing to do. And so all we have to know how does this funny random variable behaves like. A binomial random variable with exponentially many trials. Thank you. It works better. It's a binomial random variable with exponentially many trials and a probability of success which decays exponentially too. So if you look at the expectation of n to the s, where s is some positive fixed number, then there is a phase transition at the point a equals b, where a is the exponent of the number of trials and b is the exponent of the probability of success. The difference is that in the case of a larger than b, we have this parameter s at the exponent, which we don't have in the other case. So there's a phase transition. A equals b. By the way, what kind of a random variable is it? Very well known. In the limit of large n, it's nothing but a Poissonian random variable. Okay? So the intuition is simple. When a is bigger than b, we have a double exponentially fast concentration of the random variable n around its mean. So the power s of the moment is reflected here. While in the other case, we have the dominant term corresponds to n equals 1, so we get the other expression. And if we talk about the large deviation behavior of this weird random variable, then it has a very interesting formula, which we see here at the top. And the interesting case is when a is, the operator of square brackets and the plus means positive clipping, namely, whenever the argument is negative, replace it by 0. And the large deviation behavior, the other tail, is listed here. So if we apply this idea, let's begin from a simple example. For the binary symmetric channel with crossover probability P, then here we have the number of trials is the number of coordinates, e to the nr. The probability of success of falling in a given conditional type is according to the mutual information associated with this type. And we have this behavior that we see right here. And when you plug it into the expression of the probability of correct decoding, we're getting a very compact expression, which is exponentially tight. And I'll write it this way. I'll open it, the divergent. Delta GVR is the Gilbert-Varshamov distance associated with R. You can think of it as the distortion rate function of the binary symmetric source. So this is what we get. And for comparison, if you do it in the traditional way of using Jensen's inequality, namely you insert the expectation into the brackets, what you get here is the different expression. So you see here a minimum between two terms, while previously we got some weighted average between exactly the same two terms. So it's clear that the blue expression is a tighter bound. Okay. Here's an application to random binning, Slepian-Wolf. We randomly choose a bin Z according to the uniform distribution, and we have a map decoder at the other side. We search over all code words sharing the same bin, and we end up, the probability of error is associated with a type, with a Bernoulli random variable which counts how many conditionally typical X sequences given Y have the correct bin, and this is a binomial random variable with this probability of success and this number of trials. Another thing is about, if we look at Forney's 68 paper, the classical paper about erasure list decoding, which has quite a complicated decision rule, and we, instead of using the usual idea of bounding the indicator function by a power function, we apply the very same technique of the type class enumeration, and eventually we end up with something that we can deal with given the information that we already have about these random variables. So again, here there's no single step where we lose the exponential tightness. It's all exponentially tight, while in this approach, even the first step might not be tight. We don't know. Sometimes we have to deal with expressions that random variables appear also in the denominator. For instance, consider the so-called likelihood decoder, which is a randomized decoder that randomly selects a decoding based on the posterior distribution of the code word given the channel output. And we have to deal with randomness in the denominator, but this is easy to deal with the well-known identity that connects the expectation of a positive random variable with the integral of the probability of a tail of this kind. And after a while, we end up with something that we know how to deal with. Again, the summation can be written in terms of type class enumerators. So I think the idea is quite easy. And by the way, sometimes randomness in the denominator can be handled differently using what I so-called transform method. Suppose we have to deal with something like this, expectation of 1 over summation of some random variables. Then one way to handle it is to represent it as a Laplace transform of the unit step function, and then exchange the order between integration and expectation. And then you have, say in the Gaussian case, it's a Gaussian integral, which can be computed in closed form. So this is one component of my little hammers and screwdrivers. Yet another component is the analog of the method of types for infinite alphabet. So as we all know, in the finite alphabet case, the method of types applies with the following definition of a type. You can think of it in two ways. One is the set of all sequences with a given empirical distribution. And the second way is that the set of all permutations of a given sequence. Both definitions, both equivalent definitions are particular to the finite alphabet case. But an alternative way to look at it is to look at the set of all sequences x prime, which have the same probability as the given x, simultaneously for every memoryless source P. And this is a definition that easily extends to other classes of distributions, parametric classes of distribution. So we say that two sequences are of the same type if they share the same probability simultaneously for every value of the parameter. So if we look, for example, at exponential families, where we have at the exponent some linear combination of some statistics, then we can define a type by the same, but by looking at all x primes that have the same sufficient statistics as x. So in the case of finite alphabet memoryless case, it's just counting the various letters. In the Markov case, it's counting transitions. In the Gaussian case, it's look at the empirical mean and the empirical second moment. And in the autoregressive case, you look at empirical autocorrelations and so on and so forth. So the main building block of a method of types for the continuous case, we need two things. We need a computable expression for the size of the type or the volume, depending on whether it's talking about the continuous case or the discrete case. And we need that the number of different types will not be too large. So there's a difficulty that, say, at least in the continuous case, think of the Gaussian case, we have two problems. First of all, that the volume of the type is zeros. Think, for example, on zero mean IID Gaussian random variables, then the type is defined by a sphere, a hypersphere in the space R sub n. So it's a surface of a sphere, so it has volume 0. And the second thing is that the space is unbounded, so the number of types is unbounded. So the way to get around is to allow some tolerance, epsilon. So the hypersphere will become thick, they will have a volume. And the second thing is to look at some large enough but bounded region of the space, out of which the probability, the relevant probability decays exponentially fast enough that it's not interesting to look at it to begin with. So we can easily get an expression for the volume of a type just with a probabilistic, simple probabilistic argument. It's actually 1 over the maximum likelihood of the sequence. That's a way to think of it. And it gives the right exponential behavior. And we can do the same with conditional types, T of x given y, by defining an appropriate exponentially family of channels. It's exactly the same idea. So for example, if we have to assess volumes of conditional types, say for the Gaussian ISI channel, we have to deal with several kinds of statistics like the empirical correlations between the channel input and output and the autocorrelation of the input. So here we have a definition of a certain type. Again, I wrote it here briefly. Actually, there should be tolerances here too. So I represent it by an integral. The size of this type is an integral over all Rn with a product of Dirac delta functions which put all their mass on the conditions that define the type. And then we can represent each Dirac delta function by the inverse Fourier transform of the unity function. And then if we interchange integration over the frequencies with integration over Rxn, it becomes a simple Gaussian integral which you can deal with. And this is extremely important, for example, if we want to develop a universal decoder for ISI channels. So this is in the joint work with Wasim Khalikals, Sanatyan, and Briol Medard. Yet another tool from my toolbox is it's a joint work with Igal Sasson from my department, is the integral representations of certain functions like the logarithmic function. This is an identity. What we see here is an identity which is pretty well known among physicists. I think it's a bit less well known in our community. Some people that I asked, I showed them this identity. It was new to them. And it's extremely useful because in many cases we have to take expectation of the logarithmic function, so which is difficult to handle. And instead of that, we have to deal with the moment-generating function, which in many cases is much easier. For example, in many cases, this x is a summation of IID random variables yi, and then when you get to the MGF, it's just raising the power of one of them, which is easy. So this gives a very nice tool which helps us to compute things, and in the paper there are several examples of applications where we use this identity. A similar identity we have also for the power function, which I think is even less well known. And again, the same idea. We replace the power function, which is not easy to use, by the MGF of the random variables. And once again, we have many applications. Yet another, maybe the last tool that I'll discuss before giving some examples of results, is what I call the Jensen-like inequalities, with quite a recent work. As you all know, the classical proof of Jensen's inequality, you look at a family of supporting lines. You lower bound you have a convex function, f, which is this curve, and you bound the expectation from below by the expectation of, we have the family of all supporting lines, which is f of a, parameterized by a, and if you choose a equals the expectation of x, then you get the famous Jensen's inequality, that's well known. Maybe people, not all of us paid attention to the fact that this choice of a is also the optimal one. If you maximize this expression over a, then you see that a star, the best a, is the expectation of x. But this gives the idea that maybe when the function of f is not, we don't have to compute the expectation of f on its own, but it's part of a more complicated expression, say a product of two functions, f, the convex function f and another function g, or a composition of functions and so on. When f is just part of a more complicated expression, it may no longer be true that the optimal choice of the parameter is the expectation of x. And indeed, in many cases, it becomes something else. And fortunately enough, in many of those cases, we can find in closed form what is the optimal supporting line. So here is just very few examples of what I call Jensen-like inequalities that we get using these ideas. the first one, where is it? Okay. The expectation of minus x ln x. I think you all understand that it's very applicable in information theory, this function. The first term is exactly an upper bound because the function minus x ln x is concave. So the first term is an upper bound. The second term give you the gap between the upper bound and the lower bound, and it depends on the fluctuations of x, the variance of x. So we get a bound which depends not only on the expectation of x, but also on the second moment. That's not too bad, because in many cases we can also deal with second moments. Another example is the power function. This applies only for all s, but not in the interval between 1 and 2. So for s larger than 2, this is an improvement of the usual Jensen inequality applied to powers. You have here in additional terms. For s less than 1, the blue expression becomes less than 1, so, and the expectation of x raised to the power of s becomes an upper bound. So we have a variety of situations here. Yet another example is this funny function. For instance, you have a channel with a random SNR, and you want to estimate the capacity, the ergodic capacity of the CMO channel, for example, and you want not only the expectation, but also fluctuations, also the variance. So the second moment is this guy. And again, we have a function that depends not only the expectation, but also in the second moment. So in the paper, there's, of course, many other examples. Some of them also are associated with the MGF and its derivative, which in many cases are easy to handle. And sometimes we can even get reverse Jensen inequalities and bounded functions that are neither convex nor concave. And it also extends to multivariate convex functions and so on. Okay, some examples of results as time permits. The first example is list decoding. We have a code, examples of cases where I used these techniques. We have a code of e to the n r code words, randomly selected independently uniformly in a type. The channel is a DMC as usual. The index I of the transmitted message is chosen uniformly over all messages. And the decoder outputs the indices of the L most likely messages. And an error event is defined as the case where the correct index is not in the list. And I'll talk about two regimes. One of them I called the fixed list size regime, and the other one is the exponential list size. Okay. So here we have a general expression for the probability of error. Forget about all the details. The important point is that the parameter L, the list size, appears in two places. Here is one, and here is the second one. And the analysis is based on type class enumeration, where we count how many code words have likelihood that beats the correct one. And if this number exceeds the number L, then we have a list error, of course. So in the fixed list size regime, the second term in the exponent vanishes, of course, and we get a very well-known expression, which you can also find in Chisor and Kerner, and the parameter L just multiplies the second term here. This is well known. On the other hand, in the exponential case, what we have, the important factor is at the exponent. Because then, if you look at this set of pairs, x and y, its contribution to the error event is double exponentially small. So all that counts is the complementary event, and when you calculate the probability of the complementary event, you get the sphere packing exponent computed at the rate r minus lambda. And once you optimize the random coding distribution, then you get the sphere packing bound computed at r minus lambda. And I want to remind you that this is exactly a lower bound of Shannon, Gallagher, and Berlekamp. So this closes the gap. It actually shows that the Shannon, Gallagher, Berlekamp bound is tight, thanks to the type class enumeration. Another example is a Slepian-Wolf version of list decoding, a la Forney 68. So we have a pair of source sequences, x and y. X is the source to be encoded, y is side information at the decoder. We have a random binning encoder, and which works in the usual way. And we have a Forney-style decoder that for a given channel output calculates this test statistic, where the summation of the denominator is over all code words we fall in the relevant bin. Now, if this quantity exceeds the threshold of e to the nt, then we say that x hat, for a given x hat in the bin, we say that x hat is a candidate. So if there are no candidates at all, an erasure is declared. If there is exactly one candidate, then this is our decoding. And if we have more than one candidate, then we have a list. And we look at the two exponents, like in Forney's paper, 68 paper, the probability of the event, which I called E1, the event where the correct X is not a candidate. And that's called the other event, complementary one, which we trade off with. And it is easy to find examples where, using the type class enumeration method, we get tighter results than those of Forney. One of them is the case where the rate, the binary, we have a double BSS. X and Y are a double BSS. Namely, they are both binary symmetric with a BSC channel connecting between them. When R exceeds the entropy of the source, of the crossover probability, and the threshold is small enough, then we get Forney's exponent is finite, while the type class enumeration exponent is infinite, because the decoding set is, the error event is actually empty. And another case which is easy to analyze is what I call very weakly correlated sources, in analogy to very noisy channels. So the probability of crossover is almost a half. And if we look at the relevant rate and a certain threshold, then we get that Forney's exponent grows only linearly with some parameter tau, while our type class enumeration method goes quadratically. So this is yet another example. We also have the third example corresponds to what we call typical random codes. Typical random coding, I mean that we look, instead of the usual regime, where is it? The upper expression is the usual regime where we take the expectation of error probability and then compute the exponent, rather than looking at first taking the logarithm and then the expectation. That's the typical random coding distribution. Of course, the second one is always better than the first one. And the difference is that in the random coding regime, the exponent is dominated by bad codes, especially at low rates, while in the typical exponent, what is dominant is the typical codes, namely the class of codes on which the probability is concentrated. So what we have here is an exact expression for the typical exponent. I won't give it here. It's quite a complicated formula, but it's a single letter formula, which extends and also for a wider class of decoders, general stochastic decoders, and it extends the well-known paper by Barg and Forney in several directions, general DMCs and not just BSC, a wider family of decoders, and so on and so forth. And if we particularize this decoding to maximum likelihood decoding, then we get an interesting expression here that there is associated, the exponent is minimized subject to a constraint, not just a pairwise error event, that some code word X prime beats the correct one, but we also have here another term which symbolizes the typical value of the largest score of an incorrect code word. So it's the expectation, the maximum of the expectation of the score function subject to the constraint of the mutual information because we are randomly choosing only e to the nr code words. And this gives this additional term in the maximization gives us the tightness in the whole range of rates. I'll skip this technical issue. Okay, yeah, the fourth example corresponds to a joint work with my former students, Ran Averbuch, which is now called Ran Tamir. He changed his name. And what we did here is exact exponents for the weak and strong users of the broadcast channel in a degraded broadcast channel. Not only that, we also have universal decoders that achieve the exponents of both a universal decoder for both users, the weak one and the strong one. And we also have the Lagrange duals, which are what we call Gallagher-style lower bounds, which are easier to compute because the number of parameters to optimize over is smaller. And there's also further work on expurgated exponent, which is also joint work with Nir Weinberger. Finally, the last example is a weird problem of random coding where each code word is vector quantized with the motivation of being applicable to biometric identification. So the stage of randomly choosing code words and quantizing them is analogous to the stage of enrollment to the biometric system. We are training the system. And then when we activate the system for a given person which claims to be eligible, then it's the actual use of this code for decoding. So the code words are actually features of several persons which are allowed to access the system. And the question is here, how does the quantization affect the performance? So actually the relevant channel is the one that, with the dashed line, This is the vector quantized version of each code word. So the channel, the effective channel from Y to Z is the relevant one. The maximum coding rate is the mutual information between these two guys, Y and Z. And here you see at the bottom a very complicated expression of the channel. So it's not an easy problem to deal with in the first place. Nevertheless, using these techniques, we get exponentially tight bounds on the ensemble performance, also improving some earlier work by Dazothy and Draper. We also get a universal decoding, which is as good as the maximum likelihood decoder. And it is not a simple MMI decoder. It is a modified version of the MMI decoder. I'll show in a second. And it is also as good as any decoder that depends on the joint statistics of the two sequences. So here is how the ensemble is defined. For every type, input type, we choose a test channel of Y given X under some constraints. We randomly draw some exponential number of code words just above the mutual information. We give a random rank to all members of every conditional type. This is the same idea which was used also in a paper by Lapidot and Ziv in the context of a universal channel decoding. So here it's an analogous idea. And this is just to give a concrete rule for the decoding in case we have two candidates that are equally good for quantization. And it facilitates the analysis because it provides some symmetry of the random coding ensemble. So the ensemble is defined both by the random coding and the random ranking function. And we quantize every X to the vector Y, which is both in the codebook and in the conditional type, but it has the smallest rank MXY. So the important thing here is that we have a universal decoder, which is a modified version of MMI. Why do I say a modified version? Because here, this number n of Y given Z is the size of the conditional type intersected with the code. Now, if we didn't have this intersection with the code, we had only the size of the conditional type, then it would be exactly the empirical entropy of Y given Z. And then this term alpha, which is actually the exponential form of the marginal output, would become the entropy, the conditional. So we have conditional entropy minus unconditional entropy, which is minus mutual information. And we look for the minimum, which is exactly like the maximum mutual information. So in this sense, it's a modification of the MMI. So this guy achieves the same exponent as the complicated maximum likelihood exponent. How am I doing? Sorry, less than 5 minutes. So that's about it. Here is a list of a few other works where these techniques were used quite heavily. Then there are more, also some by some other people. And there are some future challenges, but once again, I want to repeat maybe the vision or the take-home message from this talk is that the idea of dealing with interdisciplinary research, even in the high level, is sometimes really beneficial also in the concrete level of importing techniques used in other communities, in this case, the community of statistical physics, to problems that are relevant to us. So that's about it. Thank you very much.
ask it, and then maybe you can repeat the question.
Oh,
Thank you for a great talk. So can you say a few words about the differences in the case of the extended method of types? You mentioned that this is different from quantization. Can you talk a little bit about the differences between this tolerance thing, the epsilon and bounding the space, the difference between that versus quantizing?
The difference is that with this method, I'm still using the structure of the parametric family. In our case, I applied it to the exponential family, which includes many cases. And now, suppose you have a distribution with an infinite support, and you quantize it, you want to use the finite alphabet version of the method of types. Then the tails of the distribution are quite big because you have only finitely many levels. So while here, the tolerance of epsilon is I'm keeping it small everywhere. Okay, so I can control the degree of precision, which you cannot do when you have a density with infinite support. So it's two things: preserving the structure, using the structure, and the precision.
A curiosity. So your integral representation of logarithm, you showed you can handle expectation of logarithm of a random variable in a nice way. And talking about statistical physics, the replica method is geared to do the same.
Right.
So can you comment on when your method is can replace the replica method?
Well, first of all, unlike the replica method, this method is completely rigorous.
Sure, I'm interested in the power of the method. So what can you recover results that are, say, non-rigorously derived through the replica method using your approach?
I don't have a particular example, but I'm sure that this can be worked out. I'm also aware of, there's a very nice paper by, I don't recall his name, some Russian name, which actually examined the replica method very, very thoroughly and shows that there are examples where the replica method fails. And one of the examples is a very useful model for statistical physics. I think it's called the Sherrington-Kirkpatrick model. The weak link is, of course, the interpolation in the replica method, where you pass from samples of a function in the integers to the continuum. And then you can do it. It's ambiguous. You can do it in infinitely many ways. So it's not clear how to do it. I personally, I don't feel comfortable with the replica method, but that's my personal problem.
any more questions?
In these methods, what if we are interested in the tightness of the prefactors as well, in addition to tightness of exponents? Can we still say something
Tightness of what again?
prefactors, like 1/squared of n times e to the minus?
Okay. So it's not the type class enumeration method, but the saddle point method that I mentioned has the power to capture also pre-exponents, because the saddle point method gives you estimates of volumes and probabilities which are tight in the sense that the ratio between the approximation and the true thing tends to 1, not to any polynomial function or not. So actually quite recently I applied it to a problem of rate distortion coding, And the pre-exponent is important because it gives you the redundancy term.
Yes.
So the main question is always how to estimate the probability that a randomly chosen code word falls in the sphere around the source sequence.
Yeah.
So if you have an exponential, not only exponentially tight, but also it captures also the pre-exponent, then you get not only the correct coding rate, which is the rate distortion function, but also the redundancy term.
Thanks. Yeah, I was aware of saddle point approximations. I was asking whether if we have the same thing for method of types like proofs, can we still get the penalty in the prefactor using this kind of decoders, for example?
I'm not sure I understood the question.
For example, universal decoder versus the maximum likelihood decoder. Can we say something about the penalty we are having in the higher order terms?
I see. That's an interesting question. I didn't look at it yet.
Thanks.
Thanks for the suggestion. Okay.